Very happy to be here and present, even though this time it is remote, but I hope there'll be a chance to do this in person. Let me just do something quick. Maybe if I do it like this, maybe a bit better. Okay, right. So I have two research interests. One is in theory of the liquid state, and in particular, properties of liquids at different parts of the phase diagram, including at high temperature and pressure. And more recently, my group and myself were trying to think how to connect different liquid properties to fundamental physical constants like the Planck constant and electron mass. The second part of what we do is related to modeling radiation damage. And that's what I was invited to talk to you about today. Right, so we're going to discuss how we can use a molecular dynamics simulation to understand radiation damage. So the main reason we want to do this is related to the problem of dealing with nuclear waste. So when the fuel in the nuclear power station gets exhausted, when it's no longer active enough to maintain a chain reaction, that usually gets taken out from the reactor. And then the problem is what to do with it. Okay, so even though it's not very active, it's for the purpose of nuclear power, it is still quite radioactive. And so what usually happens is that this waste is then that material is declared often as waste. Okay, so it has no useful purpose. Sometimes the approach is to reprocess it. But if you reprocess and then use it again, then eventually you're faced with the same problem of having to deal with what is left in the end. And the common way of handling this is we put this unwanted waste in a material. By the way, could I quickly check if you see my mouse move?
Yes.
Yes.
We
okay.
can see your screen. Yeah.
Thank you. So you put this material, this radioactive material, in a inert matrix. So, for example, in a piece of ceramic. And what's shown here is a nuclear repository. Okay, so this is where basically what we do, we melt all the, let's say we melt silicate, nuclear glass, then we mix all this material together, then we quench the melt. And now all these nuclear compounds become dispersed and immobilized in this matrix. And typically, this is a canister this of the size of meter by meter, and then we can put it somewhere and hope that it will remain intact and immobilized there for a long period of time. By intact and immobilized, we mean that this material should not diffuse out of the this nuclear waste form. Okay, so this is why it's called the waste form. Now the question is for how long, right? And that's an important question because some of the actinides in the nuclear waste are long-lived. So, for example, the half-life of uranium or plutonium is 25,000 years, at least of some of the isotopes, and that means that this material should be able to withstand radiation damage for a long period of time between 100,000 and 1 million years. Right? So we need to be able to understand this so that we can handle this problem in a safe way. Then the question becomes, what is the right choice of materials? Okay, and turns out that ceramics, okay, very much like what my ceramic cup that I'm holding here, are actually quite good because they're quite stable compared to all other materials. Okay, they don't corrode as much as, let's say, metals. and they can withstand different degrees of radiation damage. That's why we're looking at ceramic materials. In addition to understanding radiation damage in these waste forms, there is an interest in doing that in metals. That's because we are looking at radiation damage in the actual reactor, in the actual nuclear reactor at the nuclear power station, and also in the future fusion reactor. So in fusion reactors, if and when this hopefully becomes a reality, what happens is that we harvest the energy of neutrons, and there this energy of neutrons plays a twofold role. On the one hand, we get the energy out of it, right? So the material heats, and we can generate electricity, and on the other hand, it destroys the material. So under a very intense neutron flux, the metal can lose its elastic properties and, for example, fail eventually, right? So we need to be able to understand that radiation damage there. Right, okay, so this is a fairly long introduction, but I thought it might be useful to tell quickly why we are doing what we're doing. Right, so let's now talk about materials which are actually used as waste forms. So traditionally, borosilicate glasses are the ones which are used to encapsulate nuclear waste, right? So in France, for example, the big industry to use borosilicate glasses, and to some extent in the UK as well. Now, when it comes to very long-lived isotopes, like actinides, it's been realized that the series of these ceramics here actually offer quite a good alternative, because they're much more durable, and therefore they have larger ability to withstand radiation damage over a very long time. They can also incorporate high-level radioactive waste, right? So what happens is that let's say radioactive elements like strontium or barium chemically can substitute calcium in this material, or barium in this material here, okay? So chemically, these ceramics are friendly to incorporating these high-energy isotopes. And there are other classes of materials. For example, there is zirconium silicate, gadolinium zirconia, and so on and so forth, which are considered as potential waste forms. What's interesting about this zirconia system is that it's extremely resistant. So when I reviewed the field a few years ago, how do we know it's resistant? So people bombarded a thin film, so this material with very highly radioactive ions, up to very high doses, okay, involving, let's say, 10 atomic displacements for each atom. So each atom undergoes 10 displacements. And then they look at the TEM and X-ray, and they don't observe any loss of crystallinity. Right? So it's very, very resistant. And it's interesting, and it's also quite useful for the industrial applications, as I will show later. Right. So, but for now, what we need to understand is what are the effects of radiation damage and how do they affect performance of these materials, so that we can predict what happens 100,000 years down the line. And this takes me back to my PhD years. Okay, so I was like coming back to that happy time. Shown here is a natural mineral. Okay, it's a zirconium silicate. It's found as a mineral, and it's also a gem. So if you polish it, it becomes a piece of jewelry, which you can buy, in a jewelry shop. What's interesting is that when we find these materials here in nature sometimes, and in particular in Africa or in Sri Lanka, these are very old materials. These are very old minerals. Okay, some of them can be as old as 1 billion years old, right? So they are roughly as old as the Earth itself. And what happens is that during all this time, it accumulates natural radiation from uranium and thorium, which is present around this mineral in the ore deposits. And as a result, the alpha radiation from uranium and thorium gradually, but slowly but surely, destroys the crystal structure. So when we look at the X-ray picture, it is sometimes becomes completely amorphous. Right? So over billions of years, this material has accumulated enough radioactivity to destroy the crystalline lattice, and yet it looks like an intact system, right? So it hasn't fallen apart, it hasn't become dust, and for that reason, there was a proposal that maybe we can use this material to encapsulate nuclear waste. Right? So we kind of take a lesson from nature. We say, well, if this system is so resistant, then maybe it can also be used to encapsulate nuclear waste. And so we had an interesting graph plotted by my experimental colleague. What he has done here, he has collected the series of these natural zircons with various degrees of damage. So P here shows the amorphous fraction. Okay, so here, the fraction of the amorphous material in this natural zircon is 4%. Here it increases to 37%, and in heavily damaged ones, it becomes 95%. Right? So and you can see how it actually changes color across this series. And then what he does, he takes these samples and applies a solution of calcium, I think, and then he waits for the solution to penetrate inside the sample, and he plots the distance. He can observe how far this penetrates. Okay, I think he called it rim thickness, and he plots the rim thickness as a function of the fraction. I know that this graph has a logarithmic scale on the y-axis. What's interesting is that for amorphous fraction up to 30%, there's very little diffusion. Okay, so nothing changes much, but then at around 30%, it starts to increase dramatically, and then there is another large increase around 7%. Yeah. The increases of diffusion are pretty dramatic, and you can see that the changes by the several orders of magnitude. That's interesting, right? Because we, from the point of view of encapsulating nuclear waste, we can say that here, the diffusion rates are very small, right? So if you put a radioactive ion in it, it will probably not diffuse too much. On the other hand, if you put it on around here, then it will, the diffusion will be 100,000 times more, and it might actually then get out. So, but what we set to do, we set to understand why this happens here, why there is such a large increase of the energy of the diffusion. So we did molecular dynamics simulations. So for those who are not involved in this, what these simulations do, they take a system and they impose, an initial structure, and they say, well, certain systems interact via a given interaction potential. We specify this interaction potential, and we try to be quite careful at choosing the right potential. We want this potential to do a good job at representing material properties. And these days, when I was doing my PhD, to simulate a system of 10,000 atoms, I had to use state-of-the-art vector supercomputer at Cambridge University. These days, anyone can do that on their own laptop. Okay, so hardware has increased enormously in the last 20 years or so. Even then, it's a challenge to simulate very large system sizes, right? So because the recoil energies are very large, and in particular, in actinides, most of the damage comes from alpha decay, and so recoil has the energy of about 100 keV. There is also a small alpha particle flying the opposite way, but that alpha particle has a small cross section, so we don't need to worry about it too much. The primary damage comes from that heavy recoil, which has a high energy of 100 keV. Now that's 100,000 electron volts, right? And that's quite a high energy. So we need a large box of to simulate the system. Right, so I talked a little bit about potentials. We take a good care of them. Then we also need to have a code which is scalable. And by scalable, I mean that suppose we have a large supercomputer shown here, then we can assign each part of our physical system, right, part of our zircon, to a different processor on that supercomputer. And we use different types of supercomputers here. Then, of course, we also need to do something with our code, because these simulations are highly non-equilibrium. So we need to adapt them to handle these conditions. And so what I would like to do now is to show you some results. So when they say that the picture is worth 1,000 words, I think a movie is also worth 1,000 pictures. This is what happens here. What we are modeling a spontaneous alpha decay. We are looking at an alpha decay, and recoil just flies, and this is what you see. You just confirm that you see the animation actually. Yes, okay. Right, so what we are looking here is the creation of this highly amorphous cloud, okay, under the influence of this radiation damage, and we see how the structure gets locally destroyed. So this now becomes largely amorphous. Okay, so we can probably. Oh, okay, I don't know what happened here. Let me just move this. We can simulate the overlap of these events. Okay, so you can see here how these regions connect and they form connected damage structure, and we can do more and more of this and see how these connected regions join together. I'd like to make a few points, and the first is these processes are very, very fast, right? So each of these events lasts roughly 3 to 5 picoseconds. So that's 3 to 5, 10 to the minus 12 seconds, okay? And there is no experiment currently that can resolve this process, right? They're just too fast. And so that's why these simulations are very useful, because we can look at each stage in an unprecedented level of details. Secondly, this size is also fairly quite small, right? So we are here looking roughly at maybe 50 angstroms. So you can probably image that with a state-of-the-art TEM. However, you still don't get atomic resolution in those experiments, but we can, and we can look at this and we can compare them to different experiments. One thing that I'd like to note for now is that you can see how even with your eye, you can see how there's less density here in the core compared to the rim. What seems to be happening is that when this guy moves around, it kind of creates a depleted regions in its path and densified regions in the core. Okay, when all this gets overlapped, we can expect density variations, right? So we can have slightly decreased density and slightly increased density. And these are not large effects, right? So we're talking maybe about 10–20% changes of density here in the core, but when they connect, and as shown here, let me just restart my slideshow. When they connect here, what we can have a percolating cluster, right? So when there are enough of these regions, then diffusion can happen starting from one side of the sample and going all the way to the next side of the sample, right? So we now have a microscopic cluster consisting of those little amorphous regions. And what's interesting is that you probably heard about percolation thresholds, and in continuous percolation, the percolation threshold is actually 30%, right? So it's very, very close to that graph that I showed before, where the diffusion increased just at the right 30% fraction of the amorphous material. So that was our model. This is how we understood that experimental result. And actually, we thought that our model is quite useful because if it tells you how much material, how much radioactive waste you can load in the system before you start to get large increases of diffusion. Right? So in our case, it's under 30%. So hopefully that then inform the industry that these are the kind of safe values to use for nuclear waste encapsulation. And then we ask the question, why does it actually get amorphous to begin with? And so shown here is a low energy radiation damage event. And as you can see, once these chains, so basically what we're looking, these are now silicon oxygen tetrahedra, and these chains start forming. And when they're forming a stable disordered network, a bit like in window glass. And once these chains are formed, they're very difficult to break. You need very high temperature to break them. So you see that at the beginning, they were all crystalline, but then they connect, and that's it. When they connect, and you have this amorphous covalent network shown in this picture here, that's how the material becomes amorphous, okay, and becomes and gets damaged by radiation damage. So the next question we asked, what is it that makes the material amorphous or resistant to begin with? So I mentioned before that there are these amazing materials like zirconium oxide and gadolinium zirconate, which just don't get amorphized at all, right? So people bombard them with high energy. We're talking now mega electron volt and up to maybe 100 mega electron volt red ions, and they don't see that they become amorphous, right? Just pretty amazing. The question we asked, what is it the process that governs this amazing ability? And we also realized that the same exists outside the area of nuclear waste. For example, these semiconductors here, gallium nitride and zinc oxide, what of course people do, they try to dope them to alter their electronic properties. And you don't want the doping to amorphize, to destroy the system, right? And what has been realized is that if you take gallium arsenide and you bombard it, you dope it, then it becomes amorphous and disordered much more readily than gallium nitride. So gallium nitride is much more resistant to radiation damage than gallium arsenide. And the question is why, right? What is it that what kind of theory we can use to explain this? Well, it's kind of interesting by its own, but if we also figure out the governing principle, then maybe then we can use this principle to design new materials, depending on what is it that we want. Sorry? Okay, sorry, I thought there was noise. Okay. And so our first hunch was that the ability to form covalent network when we have these chains joining and then forming a stable disordered configuration is what really matters in radiation damage. We also considered other criteria, but they didn't work as well as this idea that forming a stable network is what defines resistance. So the key word here is covalency, right? So the idea is that as we have two atoms and they form a covalent bond, which means that they share electrons in between atoms somewhere in the middle, means that the system lowers its energy quite a lot by forming this covalent bond. And to break this, okay, to return back to crystal requires energy. So usually, then the higher covalency means lower resistance to radiation damage. And covalency and ionicity is something that's been discussed for a while. And actually, there is very good correlation here. So what we've done here, we have used quantum mechanical calculations to calculate a parameter which we called M, which is roughly quantifies how covalent the material is. What we realize is that we have to actually do the calculation because the empirical Pauling or Phillips scales of covalence and ionicity don't really work very well for a particular systems. And so then we plotted here materials which were very resistant and materials which were very covalent here. And we saw there is a clear difference, right? So materials which were easily amorphizable here, like for example, silica, silicon, silica, then our friend zirconium silicate, they all amorphize quite easily and they have they have low radiation resistance. Whereas these materials are actually very resistant to amorphization damage. Yeah. Right, so I forgot, it's called a Mulliken overlap population, right? So it's something that quantifies ionicity. We can also quantify something which is called ionicity, and this number Q here is the number of charge in the Voronoi polyhedra. So you can actually see to what extent the material is ionic by calculating this parameter Q. And so now if we plot them across different systems of materials, you can see that as resistance becomes larger, covalency goes down and ionicity goes up. Okay, so it's all consistent. And it's not only consistent in binary compounds, but also in ternary as well. We even made a prediction here. We told experimentalists that if you now go and do the experiments across these 3 series of oxides, you'll find resistance increasing in this sequence. So that's what they apparently found. So that was quite pleasing because we were able to guide future experimental results. What I'm going to quickly now, I don't know how much time I have left. This is now the sequence of radiation cascades, but shown in quite some detail. Okay, so we have some damage starting in the top left corner, and it propagates, and it's finally this is what we have here. And the time resolution here is quite short. It is fractions of picoseconds, right? So up to here we might be looking at 0.05 picoseconds. So we can analyze everything in quite some level of detail. So an interesting result is that if I look at the structure around 1 to 2 picoseconds, I can kind of see that the atoms which get displaced, and by atoms which I mean get displaced, are the atoms which, let's say, move more than 1 angstrom, right? So I'm looking at my all my frames, and I see that not only these amorphous atoms here got accounted as displaced, but also the crystalline lattice gets displaced. So it looks like as if the structure takes a deep breath and then pushes away the crystalline lattice away from the damage. But then what's interesting is that after 50 picoseconds, all this displacement in the crystalline lattice disappears, and you're only left with a highly disordered structure here. And we think what happens is that if you can think about this radiation cascade here as a hot liquid, right? So everything moves around very, very quickly. And when you have a hot liquid, usually liquids expand, right? Because of the thermal expansion. So everything kind of gets, it pushes the structure then outwards. And that's why we get this local expansion in the system. We also realized that this modeling can actually now give us some predictions. So what I've shown here is that I've simulated this series of radiation damage across the series of oxides. Okay, I took silicon oxide, germanium oxide, titanium oxide, MgO, and corundum. I simulated radiation damage in all of them, and then here I look at the damage at the very beginning, okay, at 1 picosecond. And you can see that there is quite a lot of damage here. But then, if I look at longer times, I see quite a dramatic difference. So in silicon and germanium, there is quite a lot of damage left at the beginning. But when I look at in titanium oxide, lots of damage disappears. Okay, lots of damage was present here, but disappeared here. And when you look at aluminum 203, you can see how this structure, the damage just disappears almost completely, right? So that's what I mentioned before. That you know, we can now look at this with our eyes and see how this damage that was introduced originally is able to recover back to crystal. These systems are then able to miraculously heal themselves from radiation damage. And that's, of course, is potentially useful for the nuclear industry, because if you have a resistant material, it gets damaged, but then it gets repaired back, right? So in that case, if it goes back to crystal, it will not have those increases of diffusion due to amorphization, which I mentioned earlier for zircon. So if we manage to come up with a system which is very resistant, that's, you know, it potentially is good news for the industry. I'm going to skip this for a bit and just show you another.
Apologies, Professor Kostya, you have 2 minutes left.
Okay, all right. So now we're looking at radiation damage in fusion reactors. Okay, so in the fusion reactors, we need to simulate very high energy, right? So this is now 14 MeV neutron, and what happens is that 14 MeV neutron eventually gets scattered by it eventually transfers energy to an iron atom, and those iron atoms have roughly 1 MeV energy. For that, we had to simulate very large systems, right? So this was done by my PhD student about 9 years ago, and she broke the world record of MD simulations. And I think that record still stands unbeaten. She was quite fearless. I was very wary to simulate, you know, systems on the order of 1 billion atoms, because who knows what kind of problems can emerge. And we did have some problems at the beginning. But she didn't know that there might be a problem, and so she didn't worry. And so then we threw this problem on a highly parallel supercomputer. So we are now having about 60,000 parallel processors simulating this just one job, right? And what I want to show here is what actually happens. Now we have 1 MeV iron atom propagating in the iron structure. Okay, and you can see how this cascade develops, how atoms get displaced, and then time step increases, so we see things happening quicker. And then this is what these are the displaced atoms which are left in the system. Now, some of those displaced atoms can recombine, and that's why we also plot defect atoms. Right, so this is now the same cascade. It kind of propagates. Lots of atoms get displaced, but then as the cascade develops, some of them recombine, and you can see how cascade then shrinks back to a structure which is now much thinner than the structure on the left. And the interesting thing is that now all these defects that we are seeing are not seen at lower energies. Okay, so people have done simulations of radiation damage at low energies, but they do not see defects that we're seeing at high energies, which means that that this is not a scalable thing, right? You can't do the small radiation damage event and then transfer them back to high energy crystals. And this is my last slide. I'm just going to show you another event, but across a different trajectory. Here we're basically just changing the angle of the incoming atom. And you can see how this cascade develops here again, how it then propagates, time step increases, we see more activity happening here, and these are all displaced atoms. As in the previous case, some of the displaced atoms recombine. And we can see how they, some of them go back to crystal, and what it leaves is the collection of defect clusters, which we can now analyze. And once we analyze them, we can make predictions as to what what potential effect they have on the future fusion reactor, right? So the big problem is whether the fusion reactor would be able to withstand this high neutron damage over the period of time of its operation, right? So now we actually can have a glimpse inside this, the core of the nuclear reactor and say, well, this is what's likely going to be happening to your iron atoms. Does this matter, right? Do these defects play any role in, let's say, changing the performance and of do they have consequences for structural properties of the reactor? Maybe yes, maybe no. But now we actually know what is happening inside, so that we can talk to material scientists who can then take this idea forward. Okay, so I'll probably run out of time here. So I'll say thank you very much again for inviting me. And if there's time for questions, then I'll be happy to answer.
Thank you very much, Professor Kostya, for your insightful speech. I think it's truly intriguing because you talk about